Welcome back, and this video tries to wrap up the digital logic conversation by pulling it all together and come up with a process where we can actually design logic circuits that accomplish a thing for us, a function for us. So that's what we're going to do. We're going to break it into 4 steps so we can kind of walk through it step by step and getting it done. So let's go ahead and go through this. So step 1 is you got to understand what is it you're designing. If you don't understand what it is you're trying to accomplish, then the rest of it doesn't make sense. As soon as you understand what is that you're trying to accomplish, first thing you got to do a system diagram. Okay, a system diagram where we show what are the inputs, what are the outputs. So everybody's clear. Typically, when we do a project, you're doing it for someone. If it's doing it for yourself, that's fine. But if you're doing it for someone else, this way they know what are the inputs that comes to your system and what are the outputs. That's done through a system diagram. The next thing you do is a truth table. And the truth table is where we say how the inputs will be used to decide what output will come out. So the first thing we did in step 1 was we did the system diagram. Step 2, we did the truth table. And if you remember, the truth table basically shows the inputs and what are the output corresponding to each one of those inputs. Then you write the expressions using and or not expressions, right? The operators you have is an or, and not, right? Those are the only operators you have. And you write the expression, and we'll talk about how you can use a truth table to write the expression. Once you've done that, then you basically use gates, physical gates, and put them in the order to get your expression implemented. Right? Let's go ahead and start with experiment 1. Experiment 1, example 1, and we are walking through this 4-step for every one of the examples. So let's go ahead and go do this is a simple example here. What it's asking us to do is design a 1-bit adder that accepts 2. So it accepts 2 inputs, inputs A and B, and each input will have 1 bit. So A can be either 0 or 1, B can be either 0 or 1, and then the sum will have a sum and a carry. So there's got to be 2 bits coming in. So for example, if I add a 1 to a 1, this is not an OR, this is an actual add. 1 plus 1 is 2, which means we can't write a 2, so I got to write a 0, and then you have a carry that comes over, and you have, so your sum, this would be your sum is 2-bit, and your inputs was 1 plus 1. If your input is 1 plus 0, then it'll be 1, and you have no carry. So that would be the answer. So that's what you want to do. So the first thing I did, I said, okay, I've got a 1-bit coming in here for the first operand, and a second 1-bit coming in for the second operand. I'm going to add them together, and I'm going to get my sum and carry. If you want, you can also, it's 2 bits, 1 bit for the least significant. So if you want to think about this is the least significant bit of the sum, this is the most significant bit of the sum. Okay, now we've kind of figured out what are the inputs, what are the outputs. We have our system diagram. Step 1 is complete. Now we got to move into step 2 and try to describe the input, the operation of our device using a truth table. So the way truth tables work, remember, we do a cross. In this case, I created a table, but typically when we're doing it by hand, we're just drawing a cross like this. And we put all the inputs on one side, outputs on the other side, and all the possible. So here is a binary 0, binary 1, binary 2, binary 3, all the possible values that A and B can take. 0 plus 0 gives me a 0, 0 plus 1 gives me a 1, 0 plus 1 gives me a 1, 1 plus 1 gives me a 2. These are all the possibilities for that. So the next step I need to do, so now I've got my truth table done. And then how do I write the expression? The expressions are written simply by walking through this thing and saying, so for this one, for example, for this output, this is an output, C, all I'm doing is looking for where the ones are. There's only one in here, and that's when A is true. If it's true, A is true, and B is true. So A has to be 1, B has to be 1. And there we go. I'm done. That's the expression for C. For S, all I have to do is that I have 2 1s, so I have to write 2 of them and OR it together. So for this one, A has to be 0, B has to be 1. So A not B, every time it's 0, you make it a not. Or the other one says A has to be true, B has to be false. Okay, so this is it. And once I have this and this, I know how to build the circuit, right? From the previous videos we've done, you know, you can draw a schematic with these expressions. I'm going to leave these expressions here so we can see it. So this is a schematic, okay? Schematic is a drawing, is a logical drawing. Notice it doesn't show physically the squares and where things are, but rather logically shows. She says, for this device, this is called a component block. This is called a component ID block, and his job is to tell you what U1 is. Here you say U1 is a 74 LS04 from your earlier work. You know this is a NOT gate. There's 6 of them in there. U2 is a AND gate, and we know there are 4 of them in there. And U3 is an OR gate, and we know there are 4 of them in there. The ground and the VCC shouldn't be on the schematic, should put it up here. So basically this is telling whoever is reading that pin 14 is connected to VCC and pin 7 is connected to ground. This way I don't have to show it on my schematic. The next thing I typically do, which helps me at least, is that what I'll do is I'll go ahead and build the switches. Remember how the switches are built is resistor, switch, ground, resistor, switch, ground, and then the connection is right next between the switch and the resistor is where you get your input. Make sure you get it from there and nothing nowhere else. And then I typically like to also invert them. So I both have a value for the input A by the switch, and at the same time, I also have A naught. And so all I simply do, I run it through a NOT gate B, and I have B naught. Now, whether I need A or B, I've got it all available here. And when I'm doing C, if you remember, C equation was the only time this would happen is A true, B and true. So we'll take A and B, run it to an AND gate. And it looks to me like we are using pin 9, looks like 9-1. I don't know why it says 9-1, but anyway, pin 9 and pin 10 of this. So how do I know this? I went to the data sheet and looked at it. And why am I using pin 10? Because 1 and 2, this is the first, I used it for that. The second one I used for the other one. And the third one I've left for this. So, and then there's yet another one available as well if I need it. So what comes out of here is A and B. That was exactly what I needed for C. I run that through my diode, the LED. This is my LED, and then run it to ground. So when this is equal to 1, this lights up, and it's 0, it lights, which turns off. So I can actually test to see whether it's working. I give it, so the test plan, if you want to write the test plan, you say, okay, give it the operand 0 and 0 and see what comes up. Okay, and for the other one, for S, for the sum bit, if you remember, was A naught B or A B naught. So all I'm doing is look at it, A naught B, and then A B naught, and then I'm ORing them together. So as you can see, this is A naught B. This is this line is A B naught, and then what comes out of here is what I'm on. And then we got it. You got your circuit done. Now, when you do a schematic for this, it's extremely important that you have all these components in here, or else you're not really doing a schematic. So you need to have the ID block showing which unit you're using. Inside here, you have to show the unit number. You have to show the pin numbers and all that. For the LED and resistor, you don't do it. For the LED and resistor, you don't do it because they're obvious. The device is pretty clear what is what. You don't have to label it. But for all the other devices, you have to label it to be complete. So that's how we do it. Let's take a look at another example just to apply. So this was our 4 steps we went through. So let's take another example that is in here. Oh, by the way, just to see if you got a wires and the wires T, that's a connection. That means A is connected to B. And in this, for the first one, for the first on the list, for this one, A is connected to B. For this, A is not connected to B because it's crossing over. So that's a T, that's a crossover. So if you want to make sure A and B are connected, then you have to put a dot on it like they did it here. So this is connected. This is not, and this is connected. Not connected. Okay. So just wanted to kind of a little bit of a notation for you to remember when you're looking at the schematic, which wire is connected to which wire and which one is not. If they don't have a dot and it's crossing over, it's not connected. But if they T, they don't have to put a dot. All right, so let's go to another example. So here is a key. They say design a 3-button that opens when at least 2 adjacent buttons are pressed. Now it gets kind of important to, when you do your system diagram, you have 3 keys. The keys, each one can be pressed or not pressed. So you have a key A, key B, and key C. And you have to tell, somebody has to tell. So in the system diagram, it's really, really important to say, does 0 mean keys depressed or does 1 mean keys depressed? Either one could be true. So you really need to specify in with your system diagram that shows the input and the output what 1 and 0 means. Now, and then also for the output, is 1 on lock or 0 on lock? Okay. So now we understand what the inputs and the outputs are. Now we can go to a truth table and describe what happens. So when we go to the, since we have 3 input, we'll have 8 possibilities. So we do our truth tables like we've always done. We'll have our input, which is A, B, and C on one side, and we have our output, which is the lock on the other side. And all the possibilities, we write it from 0, 1 to 0, 1. This is binary 0, binary 1, binary 2, all the way to binary 7. So 8 possible cases. And it says that 2 keys have to be. All right. So step one for this one would be what we need to do is we need to do a system diagram, and based on this, basically we have 2 outputs, L1 and L0, and we have 2 inputs, A1 and A0. So that's step 1. They literally gave us the truth table with this diagram they provided for us. But let's go ahead and do our own work here and see where we get to. Step 2 is to do a truth table. So step 2 is a truth table. We've got 2 inputs, A1, A0. Possibilities are 0, 0, 0, 1, 1, 0, 1, 1. Outputs are L1 and L0. And they're telling on, I'm going to basically on is equal to 1, off. Remember, you have to tell what 0 and 1 means here. A0 and L1, you don't have to say anything because 0 and 1 are 0 and 1. And so we are here. This is 1, 1, 1, 1, 1, 0, 0. And this one is 0, 0. Everywhere is off, I put a 0. Everywhere is on, I put a 1. And that's my truth table. So step 3 is to write the expressions. And my expressions for L1 is here and here. And you can say A1, A0, both not, or A1, not, A0. And as we talked before, since this is only variable that is changing. So it really doesn't matter whether A0 is 0 or 1. A1 controls everything. So I can simplify this one to A1 not and be done. And step 4 is the schematic. And now remember what we do. Oh, no, wait a minute. L0, I got to do L0 still. L0 has only one associated with it, which is A1, A0. Okay. So I got to do a schematic on this one, and I didn't end here. So the way we do schematics is that first, I see what kind of gates do I need. So I know I have two inputs. I have an A1 and I have A0. So in order to make an A1, I'll say, okay, I've got the resistor to 5 volt or VCC. Then I run it through a switch, and then that switch goes to ground. Here is my A1, and I want to make a NOT out of it, so I have it for future. So I have both A1 and A1 NOT. Okay. This is rather simple, so I don't necessarily need to invert the second one. So I do 5 volts, this switch and ground, and this will be my A0. And looking at my equations, I do not need A0 NOT, so I'm not going to base the N NOT on it. And then, so A1 NOT, this is simply becomes L1, and then A1 and A0 added together give me L0. Okay, so they want to have two diodes. So there's my LED for L1. Of course, I remember to put a ground on it so I don't burn it. And then this is going to be my L0 resistor ground. This is 1K, 1K. All the resistors we use are 1K. Okay, so that's my schematic. I'm not finished. I have to tell what device. So I'm going to have, I need to look like I need two devices. This is U1, this is U2. My U1 is 74 HC or LS04, and pin 14 is to VCC, and pin 7 is the ground. So it would be nice to put in my table to have headers. So designators here, description here, and then pin, this is VCC, and this is ground pins, okay? And then my U2 is an AND, which is 74 HC or LS or whatever you have, 08, pin 14, and pin 7, okay? That's pretty much your schematic. The only other thing you need to add is just a little something here, which says this is some sort of a LED controller. And we did this, I don't know what today is, 12/31/21. And is that did this if you want to write something in here. So that's basically a simple schematic for this particular example that we were working on. So let's go back and recap what we've talked about so far in this video. This video is a logic design process, pretty straightforward. The hardest part is figuring out what it is that you want to design. Once you figure that out, everything else falls relatively straightforward out of that. Once you decided what you want to do, and know the requirement, you draw the system diagram showing the inputs and outputs. If it's not simply ones and zero and has other meaning, make sure that meanings are conveyed as part of system diagram. Truth table, you show the relationship between input and output. You draw the cross, and on one side, on the left-hand side, you have all the inputs. On the right-hand side, you have the outputs. Make sure you put your inputs in the binary sequence from 0 to 7. Write the expression for each of the output expressions, and then use the gates and or not to implement those expressions on a schematic. Make sure your schematics has an ID block. Make sure every component is identified. Every component has an input and output pin numbers on it. And then make sure you have an ID block with the author's name and the date and the revision or anything else on it, and you're good to go. And that concludes the digital design portion of the video series. Thanks for watching.